Welcome to the practice set for lesson 6-2 in Physics 1. Problem 1 says, how much work is required to stop an electron, which is moving with the speed of 1.10 times 10 to the power of 6 meters per second, given that the mass of the electron is 9.11 times 10 to the negative 31 kilograms. All right, so it's asking how much work is required. In order to calculate how much work is required, we're going to go ahead and recall the work energy principle. This work energy principle says that work is going to be equal to the final kinetic energy. We'll say kinetic energy sub final minus the initial kinetic energy. Now, what's special about this problem is that we want to bring the electron to a complete stop. And any object that is at a complete stop or has zero velocity will have zero kinetic energy. So the final kinetic energy will just be 0. So it's going to be 0 minus the initial kinetic energy. So what's going to happen is we're going to have some negative work here because we're bringing an object that was in motion down to no motion. All right, so our answer is going to be whatever value we get for our initial kinetic energy, but with a minus sign in front. And hopefully you can see that very clearly here, given the work energy principle. All right, so let's go ahead and solve for the kinetic energy. We know that any kinetic energy, the quantitative definition for any kinetic energy is this. So Ke is equal to 1/2 mv squared. And I know I said any kinetic energy, but I mean mechanical kinetic energy. In this case, especially translational mechanical kinetic energy, which is what we're dealing with here. And the simple part about this question is that the velocity and the mass are given for this point. So I'm going to go ahead and just plug that in. That's equal to 1/2 1.1. Actually, let's go ahead and plug in the mass first. The mass is 9.11 times 10 to the negative 31 kg. And then we're going to multiply that by the square of 1.1 times 10 to the power of 6 meters per second. So we're going to square that quantity. All right, if you go ahead and just take these two values, or these three factors, the 1/2 included, and put them all into a calculator, then you should get something similar to 5.51. Yes, we're dealing with three significant figures, so 5.51 times 10 to the power of negative 19. All right, so kilograms times meters squared per second squared should give you joules. Okay, that's going to end up being, if you want to look at it that way, newtons times meters, which is exactly what we need in order to have some work. And so what we're going to see is that our initial kinetic energy was this many joules. All right, and we know from the work energy principle that the work done to bring it down to 0 meters per second, to bring the electron down to 0 meters per second, is just going to be the 0 minus that amount. So the answer is just going to be negative 5.51 times 10 to the negative 19 joules. Problem 2 says an 85-gram arrow is fired from a bow whose string exerts an average force of 105 newtons on the arrow over a distance of 75 centimeters. What is the speed of the arrow as it leaves the bow? So first off, I noticed that I have a few quantities here that are not in SI. They're close to SI, so I want to take the mass of that arrow to be in kilograms. So instead of 85 grams, I know that there's 1,000 grams in a kilogram, so I'm going to move the decimal place over 3 spots. And I'm going to say that we have a mass here of 0.085 kg. And that's going to be the mass of the arrow. Now, also, we have a displacement going on here, and that displacement is going to be the displacement that the arrow experiences from the time that the arrow is shot to the time that it actually leaves the bow. And that's going to be 75 centimeters. I'm going to put in a lowercase d. And because there are 100 centimeters in a meter, I'm going to go ahead and just move the decimal place over twice there. I'm going to say that's 0.75 meters. All right, so we have everything in SI because we have 105 newtons, which is a compound SI unit, so we're good to go with that. And the question is asking, what is the speed that the arrow has when it leaves the bow? Well, I think this probably would have been a difficult question before introducing the work energy principle, but now that we have a quantitative definition for work and we know the work energy principle, along with a quantitative definition for kinetic energy, I think we have everything we need in order to go ahead and solve this problem. So first off, reminding us of our quantitative definition for work, we have that work is equal to force parallel to an object's displacement times the displacement itself. And so we're going to assume that that 105 newtons is that parallel force being applied to the arrow. And then the 0.75 meters is going to be the displacement we're dealing with if we're trying to calculate how much work that the bowstring did on the arrow. So let's actually calculate that really quick. We have work is equal to 105 newtons times 0.75 meters. And if we're taking this to two significant figures, then that should bring us to about 78 it should bring us to about 79 joules. All right. So the amount of work that the bowstring did on the arrow was about 79 joules of work. And if we take this information and we recall the work energy principle, the work energy principle, of course, being that work is equal to the change in an object's kinetic energy. Okay, and when I say change in kinetic energy, I mean its final kinetic energy minus its initial kinetic energy. And the thing is that we already know, or we should make a mental note at this point, that conceptually, the arrow's initial kinetic energy was 0 if you were holding it to fire because it was not moving. So then we can strike out that initial kinetic energy, and all we're really looking for in our work energy principle is the final kinetic energy of the arrow. That's going to be equal to the change if we started at 0. That said, we have a quantitative definition for kinetic energy. That quantitative definition for kinetic energy, which we have here in orange, is 1/2 mv squared. And that's really what we're looking for, because now we have something that has velocity in it. And that's really what we're trying to answer here. What's the speed of the arrow? So we know how much work the bow did on the arrow. It was 79 joules, or it was roughly 79 joules. And so I'm going to set those 79 joules equal to the final kinetic energy of the arrow, which is what the work energy principle is telling us to do. So I'm going to set that equal to 1/2 mv squared. And before I plug anything in, I know I'm already looking for velocity. So I'm just going to solve algebraically for velocity first before I plug, the mass in and start to use the calculator. So I'm going to multiply both sides by 2, and I'm going to divide both sides by mass. From there, I'm going to take the square root, and I'll show you exactly why. When I multiply both sides by 2, take 79 times 2. All right, we're going to have 158 joules. And this is the reason why I multiplied both sides by 2. I want to get rid of that 1/2. So 158 joules, dividing both sides by mass. Oops, sorry guys. Dividing both sides by mass, and then taking the square root is going to give us v isolated, and we had to take the square root after dividing mass out because we have v squared, and we don't want v squared, we just want v. So now we have what we need over here on the left side. Okay, so what we can do is we can plug in now the mass of the arrow and then just calculate it all out. So 158 joules divided by 0.085 kilograms, and we take the square root of that value. What we're going to get is about 43 newtons. Let me get that pencil out. It's going to be about 43. Did I say newtons? I meant to say meters per second. About 43 meters per second. And that's the velocity that's going to create our final kinetic energy, and it's also going to be the velocity that the arrow is going to have after the 75 centimeter displacement. And in other words, it's the velocity that the arrow will have when it leaves the bow. Question 3 is almost more of a conceptual problem than it is a quantitative problem. It says, if the speed of a car is increased by 50%, by what factor will its minimum braking distance be increased, assuming all else is the same, especially if we ignore the driver's reaction time? All right, so it's asking, what is the distance that will be required in order to brake, assuming all else is the same? Okay, so the work energy theorem states that the work done by the force is equal to change in the kinetic energy of the car. All right, so what I'm saying here is that work is equal to the final kinetic energy minus the initial kinetic energy. And we know that because we're trying to get it to stop, that the final kinetic energy is going to be 0. So that means that at least the magnitude of the work required is going to be equal to the initial kinetic energy. Right? So what we're saying is that if the car's speed was something, then it requires some amount of kinetic energy in the form of work to stop it. And if its velocity increased by 50%, then it would require more kinetic energy or work to stop it. But how much more exactly? Well, let's check it out really quick, because we know quantitatively that kinetic energy is defined as 1/2 mv squared. And that's v, the velocity of the object, or in this case, the car. So if it was this kinetic energy, if we're trying to get it to stop where our final kinetic energy is 0, then the magnitude of this kinetic energy is equal to the work required to stop it. Now, it will be negative work, but the magnitude of that work is equal to 1/2 mv squared for whatever initial velocity or whatever initial kinetic energy we have. So then the work required to stop it if velocity was 50% more is simply this. Okay, it's going to be, watch what I do here. Kinetic energy is equal to, and this is for a new kinetic energy, for the 50% faster velocity, it's going to be equal to 1/2 m, and then inside here I'm going to do 1.5 times velocity, because that's going to give me a velocity that's 50% greater than my original velocity, and I'm going to square this. And that's two factors inside of a quantity that's squared, so I can square them independently. Like I can square them individually. So 1.5 squared actually gives me a coefficient of 2.25. Right, so I can actually pull that completely out of the expression and say that the kinetic energy of a car going 50% faster, or an object going 50% faster, is going to be 1.5 squared is 2.25 times your 1/2 mv squared. And what I'm saying is that if you increase your velocity by 50%, then you're increasing your kinetic energy by 2.25 times. All right, and that's simply because 1.5 squared is 2.25, right? And because this is all equal to the work required, we know that the quantitative definition for work is force times distance. All right? So what I'm saying is, because 2.25 is just a factor I can multiply the work by, it could be just multiplied here as well. All right, so if it was, the original work was FD, all right, then the new work is going to be 2.25 FD. And we could very easily multiply that 2.25 by the distance, telling us that, well, how much is the distance going to increase if we increase our velocity by 50%? Well, that distance, that stopping distance, is going to be 2.25 times longer, because our kinetic energy is 2.25 times bigger. So the answer is 2.25. Welcome to problem 4. This is a level 3 problem, but I think it's kind of fun, especially with all the equation building that's required. So let's get started. One car has twice the mass of a second car, but only half as much kinetic energy. When both cars increase their speed by 8 meters per second, then they have the same kinetic energy. What were the original speeds of the cars? So I'm going to go ahead and start off just focusing on the first part of the first sentence. One car has twice the mass of the second car. So what that's telling me is that if car 1 has mass 1, okay, that's going to be equal to 2 mass 2s, if mass 2 is the mass of the second car. It takes 2 masses of the second car to equal the mass of the first car, because car 1 has twice the mass of car 2. At the same time, it only has half as much kinetic energy. Okay, so in this case, kinetic energy of car 1 is going to be equal to half the kinetic energy of car 2. All right, so kinetic energy 1, or the kinetic energy of car 1, is half as much as the kinetic energy of car 2. So kinetic energy 1 is equal to 1/2 kinetic energy 2. All right, so let's go ahead and use that. And also the fact that we have a quantitative definition for kinetic energy, that is just this. I'll show you. Ke is equal to 1/2 mv squared. All right, we're going to use that a lot in this problem. And first off, we're going to start off by just actually plugging this expression in for both of our kinetic energies. All right, so I'm going to start on the left side of the screen here. Let's do it in orange. We can say that kinetic energy 1 is 1/2 m1 v1 squared. And we're going to set that equal to, sorry about that. We're going to set that equal to 1/2 m2 v2 squared. Now, that's actually not quite true yet because we have here that the relationship is this. So it's going to be an extra 1/2 in there. 1/2 times the kinetic energy of 2. All right, so now this expression here in orange is the same as the expression here in blue, just with our expression for kinetic energy plugged in. Now, I'm also going to use this relationship, and I'm going to plug 2m2 in for m1. All right, so when I do that, it's going to look like this. 1/2 2m2 v1 squared is equal to, and I'm going to go ahead and distribute this 1/2, so it's going to be 1/4 m2 v2 squared. And the reason why I wanted to do that, is because since there's only one term on each side, I can get rid of similar factors. So I can get rid of m2 on both sides now, and that's really useful because I'm looking for velocity. That said, I now have, if I go ahead and distribute this 1/2 with the 2, I just have v1 squared on the left side. And v1 squared is going to be equal to 1/4 v2 squared. All right, now to get rid of that ratio, I'm going to go ahead and multiply both sides by 4, and that's going to give me 4 v1 squared is equal to v2 squared. All right, and now to get rid of the now to get rid of the square, I'm going to take the square root of both sides. The square root of 4 is 2, and the square root of v1 squared is just v1, and that's going to be equal to v2. And now we have a relationship about the velocity of car 1 and the velocity of car 2 if that first sentence is true in our question. So now we know that the velocity of car 1 must have been the velocity of car 2 must have been twice as much as the velocity of car 1 because the velocity of car 2 is equal to 2 velocities of car 1. All right, good. Let's actually keep that information. That's the most important thing about what we've done here, and I'm going to go ahead and clear our screen a little bit so that we can continue on looking for those initial velocities. Now, we have some more information. It says when both cars increase their speed by 8 meters per second, then they have the same kinetic energy. Okay, so that means there's some second kinetic energy for each. We'll call it kinetic energy prime for 1 is equal to kinetic energy prime for 2. And that's going to only be equal when we have 1/2 m v squared, but instead of just v squared, it's going to be v plus 8 squared, and that's going to be equal to 1/2. So of course we need to write m1 there. 1/2 m2 v2 plus 8 squared. And the reason why I wrote it like this, and I can actually clean this up a little bit, because we need that to be 1/2 m1. The reason why I wrote it like this is because it says when both cars increase their speed by 8, they have the same kinetic energy. So in order for these to be the same without the extra 1/2 in there, then we need to actually increase the velocity of each of them by 8 meters per second. Okay? So from here, I can go ahead and still plug in what we know for about the relationship between m1 and m2. So I'm going to go ahead and say that 1/2, and then in parentheses here, 2m2 times v1 plus 8, that is, squared, is equal to 1/2 m2 v2 plus 8 squared. All right. Just like before, I can go ahead and cancel that m2. And then I have that V1 plus 8, because this is going to cancel as well. I have V1 plus 8 squared is equal to 1/2 V2 plus 8 squared. Now, I have a relationship about how V1 and V2 relate to each other, so I can go ahead and plug that in for one of these, all right? And I'm going to go ahead and plug that V2 is equal to 2V1. And so let me rewrite the next step. It's going to be V1 plus 8 squared is equal to 1/2, and this is going to be 2V1 plus 8 squared. All right, this is great so far. All right, because now I can cancel that. And let's actually move this up a little bit so that we can keep working. Let's move that there. Now that I can cancel that 1/2 and that 2, or actually, no, I can't quite cancel that 1/2 and that 2 just yet. I'm going to go ahead and multiply both sides by 2. That's going to give me 2V1 plus 8 squared is equal to 2V1 plus 8 squared. And from this point, I'm going to go ahead and take the square root of both sides. So if I take the square root of both sides, that's going to give me square root of 2 times V1 plus 8 is equal to 2V1 plus 8. All right. All right, so from there, let's keep working. I now have root 2V1 plus root 2, 8. Root 2, 8 is equal to 2V1 plus 8. All right, so that's a multiplication sign right there, just in case we weren't sure. All right, and I can move my V1s to one side, and then I can move my constants to the other side, and that's going to be root 2V1 minus 2V1 is equal to negative root 2 times 8 plus 8. And then I can factor out a V1 here, so I have V1 times root 2 minus 2 is equal to whatever this is all equal to, and if we go ahead and grab a calculator, we can solve that pretty quickly. We could say that negative root 2 times 8 plus 8 is equal to negative 3.31, roughly. And then that root 2 minus 2 is equal to negative 0.58 V1. So, and if we go ahead and divide both sides by that negative 0.58, we'll get that V1 is roughly equal to 5.7 meters per second. All right, so that's our first answer. We know that V1, we know what V1 is now. All right, that's going to be super important to us. All right, now I'm going to go ahead and get rid of a lot of this. All right, and now that we know what V1 is, we can actually plug that into the same thing again to go ahead and solve for V2. So we're gonna basically do that round over again, but we're gonna plug in an actual number for V1. And when we plug in that number for V1, and we plug in 2m for2m2 for m1, we can get rid of our m's. Then the only variable we'll have left is V2, and then algebraically we'll just solve for V2 from there. All right, guys, good luck finishing that off. Happy studying, and I'll see you guys in the next one.